Okay, let's start. Let's discuss about artificial neural networks.
Absolutely. Let's dive in. We'll go step by step. So, to get us started, let me ask you, what do you understand so far about what an artificial neural network actually is from first principles? Let's build on what you know, and we'll expand from there.
So, as I understand it, there are multiple neurons in each layer. Um, the input is broken down
It's
into
3 o'clock.
fundamental parts, and each fundamental part or subpart is mapped to one specific neuron. This gets passed down to subsequent layers where more complex structures get formed from these fundamental parts, and after passing through multiple layers, it goes on to constructing the macro part or the macro item itself.
That's a really good starting point. You've got the right intuition that a neural network is built up from these layers of neurons, and each layer gradually forms more complex representations. So let's break it down a bit more. Why do you think having multiple layers might help the network understand something more complicated than just having one layer of neurons would?
So, giving it multiple layers helps bring together the information from the previous layer using multiple combinations, which would not have been possible if it was just using a single flat layer where it would just map out individual items or individual subparts based on their individual properties. By having multiple layers, we are actually combining these properties with variable degree of separation or a variable degree of correlation. Is that a right way to think about it?
Yes, you're definitely on the right track. Exactly. By adding multiple layers, what you're doing is letting the network create combinations of features step by step. Each layer takes the simpler patterns from the previous layer and combines them into more complex patterns. So instead of just recognizing, let's say, edges or very simple textures, it can start to recognize shapes, then more complex structures, and eventually something really high level, like an entire object. Now let me ask you this to keep us going Socratically. What do you think is the role of the activation function in each of these neurons as we go deeper through the layers?
It optimizes the function so that it recognizes that specific part of the object or parameter better.
Exactly, you're getting the hang of it. The activation function is really what gives the network its ability to learn these complex patterns. So if we just had a bunch of layers without activation functions, all we'd be doing is stacking linear transformations, and we wouldn't actually get that non-linearity that lets the network learn more interesting things. So yes, the activation function's like a little switch that lets the neuron decide, is this pattern worth paying attention to? Do I fire or not? And that helps the network build up those complex representations layer by layer. All right, let's keep it going.
Yeah, you had mentioned regarding linear versus non-linear. Can you explain a bit more on that?
Absolutely. So let's unpack that a bit. When we say something is linear, we just mean that whatever the network is doing is kind of like a straight line relationship. If you only had linear layers, you could just squash them all down into one big linear transformation. It wouldn't really matter how many layers you had. We'll just end up with one big linear function. Now the magic really comes in when you add these non-linear activation functions. That lets the network start to learn much more complex, curved, and interesting relationships. Each layer, with its own nonlinear activations, lets you stack up these building blocks into something that can approximate really complicated patterns. So that's why neural networks are so powerful. That nonlinearity is the secret sauce that lets them learn all these intricate things from the data. So yeah, you're definitely on the right path.
The non-linearity, can you expand a bit more on that with some examples?
Of course. Let's dig a bit deeper into that. So when we talk about nonlinearity in a neural network, what we really mean is that the activation functions are what let the network model things that aren't just straight line relationships. For example, one really common activation function is called the ReLU, which stands for rectified linear unit. It's super simple. It just says if the input is positive, keep it as it is, and if it's negative, just turn it into 0. That might sound really basic, but just that little nonlinearity, just that little bend, lets the network piece together all sorts of complicated shapes and patterns when it's learning. So instead of just fitting a straight line through the data, you can imagine it can fit curves, it can fit more complex surfaces, and it can really learn these nuanced patterns in the data. So in short, those nonlinearities are what let the network go from just simple flat predictions to something really rich and complex. And that's why neural networks can do such cool stuff.
Okay, interesting. Anything else that we should cover?
I think we've covered some really solid ground so far. We talked about how multiple layers help build up complexity and how that nonlinearity from activation functions lets the network learn more interesting patterns. But of course, there's a lot more we can dig into in future discussions, like how training works, what backpropagation is, or even how to think about different architectures. But I think for today, you've got a really nice foundational intuition, and we can definitely keep building on that next time.
Okay, thank you so much.